In electrical systems, particularly in environments like schools, assuming the potential existence of parallel current paths is prudent, even when obvious metallic connections are not visible. Schools often contain diverse utility and communication systems that can inadvertently create alternative pathways for current flow. Let's examine potential parallel current paths more closely. Firstly, we'll consider obvious paths such as the water service, natural gas lines, and circuits common to multiple buildings, such as those powering house lights. Secondly, we'll look at less obvious paths which might include cast iron plumbing, particularly if it is connected to the water service. Grounded conductors from communication systems such as phone lines, alarm systems, and signaling circuits that are common to multiple buildings can also create parallel paths. Structural steel or other conductive materials interconnected between buildings also present a potential pathway. To thoroughly assess the potential for parallel paths, a detailed conductive path analysis should be undertaken. This analysis involves identifying all possible connections between the building in question and any other buildings or systems that could facilitate current flow. Both metallic and non-metallic materials must be considered during this analysis. Installing an equipment grounding conductor, abbreviated EGC, offers several significant benefits. Firstly, safety. An EGC provides a dedicated route for fault currents to return to the source. This prevents the development of dangerous voltages on equipment enclosures. Secondly, compliance with code. The National Electrical Code, often referred to as NEC, mandates the installation of an EGC in many applications, particularly in schools and commercial buildings. Thirdly, elimination of parallel paths. An EGC isolates the grounding system from the neutral system. This removes the potential for parallel paths that can compromise safety and equipment performance. Fourthly, improved grounding resistance. An EGC provides a low resistance path for grounding, which ensures proper grounding of equipment and reduces the risk of electrical shocks. Given the potential for parallel current paths in environments like schools, installing an EGC is a prudent measure. This conductor delivers a dedicated and safe pathway for fault currents, mitigates the risk of parallel paths, and enhances the overall safety and reliability of the electrical system. Now, let's delve deeper into the function and importance of each of these aspects, starting with a closer look at parallel current paths. Parallel current paths emerge when electricity has more than one route to return to its source. In an ideal electrical system, current should flow only through the intended circuit conductors, such as the hot and neutral wires. However, unintended pathways can form through various conductive materials or systems. These parallel paths can carry a portion of the current, leading to several problems. One of the primary concerns is the potential for increased resistance and impedance in the unintended pathways. These pathways are often not designed to carry electrical current, leading to overheating and potential fire hazards. Parallel currents can also interfere with the proper operation of sensitive electronic equipment. These currents can induce noise and distortion in signal circuits, leading to malfunctions or inaccurate readings. Moreover, the presence of parallel paths can make it difficult to troubleshoot electrical problems. Because current is flowing through unintended pathways, standard testing procedures may not accurately identify the source of the problem. Now, let's turn our attention to the role and function of an EGC. An equipment grounding conductor is a dedicated conductor that provides a low impedance path for fault currents to return to the source. It is typically a copper or aluminum wire that is connected to the equipment enclosure and bonded to the grounding electrode system. In the event of a fault, such as a short circuit, the EGC provides a pathway for the fault current to quickly return to the source, tripping a circuit breaker or fuse and de-energizing the circuit. This rapid clearing of the fault prevents dangerous voltages from developing on equipment enclosures, reducing the risk of electrical shock. The EGC also helps to equalize the potential between different equipment enclosures and the grounding electrode system. This minimizes the risk of stray voltages in ground loops, which can interfere with the operation of sensitive electronic equipment. It's crucial to distinguish between the EGC and the neutral conductor. While both conductors are connected to the grounding electrode system, they serve different purposes. The neutral conductor carries the normal unbalanced current in a circuit, while the EGC carries fault currents only. In a properly grounded system, the neutral conductor is isolated from the equipment enclosures, preventing the flow of normal operating current through the grounding system. The NEC provides specific requirements for the size and installation of EGC. These requirements are designed to ensure that the EGC has sufficient capacity to carry fault currents and to provide a low impedance path for grounding. Section 250.122 of the NEC, for example, specifies the minimum size of the EGC based on the rating of the overcurrent protective device protecting the circuit. Now let's examine the specific benefits of installing an EGC in a school environment. Schools often have complex electrical systems that serve a variety of loads, including lighting, HVAC equipment, computers, and other electronic devices. The presence of numerous interconnected buildings and systems increases the likelihood of parallel current paths. In addition, schools often have a large number of students and staff, making electrical safety a top priority. Installing an EGC in a school provides a dedicated path for fault currents to return to the source, protecting students and staff from the risk of electrical shock. It also helps to prevent damage to sensitive electronic equipment, ensuring that school operations are not disrupted by electrical problems. Furthermore, compliance with the NEC is essential for ensuring the safety of school electrical systems. The NEC requires the installation of an EGC in many applications, including schools, and failure to comply with these requirements can result in fines and penalties. One example of a situation where an EGC is particularly important in a school is in the installation of computer equipment. Computers are sensitive to voltage fluctuations and ground loops, which can cause malfunctions or data loss. Installing an EGC provides a stable and reliable grounding system for computer equipment, protecting it from these problems. Another example is in the installation of lighting systems. Lighting systems often have long runs of wiring, which can increase the risk of voltage drop and ground loops. An EGC helps to minimize these problems by providing a low impedance path for grounding. In addition to the specific benefits mentioned above, installing an EGC in a school also provides several general benefits. It improves the overall reliability of the electrical system, reduces the risk of electrical fires, and makes it easier to troubleshoot electrical problems. Now, let's consider a specific example of how parallel current paths can form in a school environment. Imagine a school that has two buildings connected by an underground water pipe. The water pipe is made of cast iron, which is a conductive material. If the electrical system in one building is not properly grounded, a portion of the current can flow through the water pipe to the other building. This parallel path can cause the water pipe to become energized, creating a shock hazard. It can also interfere with the operation of sensitive electronic equipment in both buildings. Installing an EGC in both buildings would provide a dedicated path for fault currents to return to the source, preventing the formation of this parallel path. Let's delve a little deeper into the NEC requirements for grounding and bonding. Article 250 of the NEC provides comprehensive requirements for grounding and bonding electrical systems. These requirements are designed to ensure that electrical systems are properly grounded and bonded, minimizing the risk of electrical shock and fire. Section 250.4 outlines the general requirements for grounding electrical systems. It requires that all electrical systems be grounded in a manner that will limit the voltage to ground and facilitate the operation of overcurrent protective devices. Section 250.24 provides specific requirements for grounding separately derived systems such as generators and transformers. It requires that these systems be grounded at the source and that a grounding electrode conductor be run to the grounding electrode system. Section 250.50 outlines the requirements for grounding electrode systems. It requires that all grounding electrodes be bonded together to form a single grounding electrode system. Section 250.104 provides requirements for bonding metal piping systems and other metal objects that are likely to become energized. It requires that these objects be bonded to the grounding electrode system to prevent them from becoming a shock hazard. These are just a few of the many NEC requirements for grounding and bonding electrical systems. It is essential to consult the NEC for complete and up-to-date information on these requirements. In addition to the NEC, there are other standards and guidelines that provide information on grounding and bonding electrical systems. The Institute of Electrical and Electronics Engineers, referred to as IEE, publishes a variety of standards on grounding and bonding, including IEE Standard 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems. This standard provides detailed information on the design and installation of grounding systems for industrial and commercial facilities. The National Fire Protection Association, often called NFPA, also publishes guidelines on grounding and bonding, including NFPA 70B, Recommended Practice for Electrical Equipment Maintenance. This guideline provides information on the maintenance of grounding systems and the detection of grounding problems. It's important to consult these standards and guidelines in addition to the NEC to ensure that electrical systems are properly grounded and bonded. Let's shift our focus to the practical aspects of installing an EGC. When installing an EGC, it is essential to use the correct size and type of conductor. The size of the EGC is determined by the rating of the overcurrent protective device protecting the circuit. The type of EGC is determined by the application. For example, a copper EGC is typically used in corrosive environments, while an aluminum EGC is typically used in dry environments. It is also essential to properly terminate the EGC. The EGC should be connected to the equipment enclosure and the grounding electrode system using approved connectors. The connections should be tight and corrosion resistant. When installing an EGC in a conduit, it is essential to bond the conduit to the equipment enclosure and the grounding electrode system. This ensures that the conduit provides a low impedance path for fault currents to return to the source. When installing an EGC in a cable, it is essential to properly support the cable. The cable should be supported at regular intervals to prevent it from sagging or becoming damaged. It is also important to protect the EGC from physical damage. The EGC should be installed in a location where it is not likely to be damaged by impact or abrasion. After installing an EGC, it is essential to test it to ensure that it is functioning properly. The resistance of the EGC should be measured using a low resistance ohmmeter. The resistance should be low enough to provide a low impedance path for fault currents to return to the source. If the resistance is too high, the EGC should be inspected for loose connections or corrosion. In conclusion, installing an EGC is a crucial step in ensuring the safety and reliability of electrical systems, particularly in environments like schools. By providing a dedicated path for fault currents to return to the source, the EGC protects people and equipment from the hazards of electrical shock and fire. Compliance with the NEC and other relevant standards is essential for ensuring that EGC are properly installed and maintained. A thorough understanding of grounding and bonding principles is vital for all electricians and electrical engineers involved in the design, installation, and maintenance of electrical systems. Understanding these grounding principles along with bonding techniques and electrical code compliance are paramount for ensuring electrical safety.